Alright, this video is going to discuss the idea of exponentials. And this is an example here on the first page of a place where you might see an exponential. Julie accepts all the friend requests that she receives on Facebook. For every friend she accepts, she tends to find two more friends that ask to be her friend. So there's sort of two referenced friends. As she is always busy with homework, she only checks Facebook once a day, always a good idea. And in order to accept those new requests. So every day she's basically accepting twice as many requests that she did the day before. For every friend she accepts, the next day she gets two more referred friends, or sort of picks up two more friends per friend. So on day one, she essentially accepts that first friend. She's got one friend right there. But on day two, that one friend refers two friends to her. So she's got two friends on that day that she's going to pick up. Now each of those friends is going to refer two more friends. So that's 2 plus 2, or basically she's going to have 4 friends the next day. Those 4 friends again, for every one I'm getting 2, so that's 2 plus 2 plus 2 plus 2, or essentially 8 friends. Then it's going to become 16 and 32 and 64 and 128, basically doubling every time. Now you can look at that as saying times 2 times 2 times 2 times 2, but the big idea is, how do you multiply by 2 over and over and over again? Well, you use an exponential. Or basically, if you think about it, 2 is 2 to the first, 4 is 2 squared, and so forth, and so on. We're basically just getting more and more powers of 2. So if I wanted to find a formula for this, I could say that the number of friends that she has, f, equals the fact that she started off with one friend, right? But then took that times 2 over and over and over again, or 2 to the nth power. Now the only problem we're going to have there is if I plug in 1 for n, that's 2 to the first, and I'm automatically going to start off at 2, or 2 to the first power. Problem is, 1 is only 2 to the 0 power. So if I subtract 1 from that, you'll quickly find a formula that will actually give you the exact correct number of people. So on the 7th day, well, 7 minus 1 is 6, and 2 to the 6th power is actually 64. Approximately how many friends would she gain on the 30th day, or after about a month? Well, big idea then is that's 2 to the 30 minus 1, or 29th power. And if we go on our calculator real quick and say 2 raised to the 29th power, we'll find out that 536870912. 5368, sorry, my memory's not so great there, 70912. 70912. After only 30 days, if she keeps accepting twice as many friends every single day, basically she'll have 870,912 friends. Approximately how many friends would she have total on the 30th day? Well, in order to get that, remember, we're going to have to add up this previous number to what she had on the 29th day and the 28th day and 27th day, and just realize that right now she's going to end up with a lot of friends. All right? So I'll let you handle that if you want to go find that number. The big idea is we're using what's called an exponential growth function. And in order to have an exponential growth function, you basically need two major parts. Number one, an initial amount, such as Julie, who started off with one friend. That's that a that's out in front. Realize that a can't equal 0, or else it would be 0 times b, and the whole thing is going to end up equal to 0. 0 times, I should say, b to the x. Remember, exponents come before multiplying. Now your growth factor, as we call it, is the b, or also called the base. A great reason to call it b. B to the power of x is really the key behind an exponential growth function. So over here at the right, I've got a couple of problems where you can identify a, remember, is that front number, or the 3 here. 3 halves being greater than 1. Notice if b is greater than 1, that means I'm multiplying by something greater than 1, and I'm going to grow. My exponential problem is going to grow by 1.5 every time. If there is no number out in front of your base, notice the base here, 2 is still to the x power, so that's your b. But if there's nothing in front, remember, that's just a 1, or multiplying by 1 there. outside of that exponent. Down at the bottom, a great way to help you with graphing is going to be to think about what are easy points to find. And the y-intercept for a basic exponential function is usually an easy point to find. Remember that for y-intercepts, x equals 0, and any exponent equal to 0 means that 3 to the half, or 3 halves to the 0 turns to a 1, and 3 times 1 is just 3. Same thing, 2 to the 0 equals 1, and negative 8 times 12 to the 0. Well, 12 to the 0 is 1, you just get that negative 8. And notice that the number that was out in front for that exponential function, the 3, the 1, the negative 8, those end up being your y-intercept. So instead of initial amount, you could also think of this as sort of being that y-intercept, again, for a basic exponential function. That's going to change here in just a minute if we slide things around a bit. But as long as we're talking about basic functions, let's talk about how to graph them. And that's going to actually be a fairly simple process. I want to think of the two easiest points that I can plot. 2 points basically define an exponential function, as long as you also know where the asymptote is. We'll talk about that more in just a second. The two easiest exponents to ever use are 0 and 1. Remember, 2 to the 0 equals 1, and 2 to the first power would just be equal to 2, which gives you a 0, 1, and a 2, 1. And that means that up to the right, I'm going to be rising. Now, finding more points is not a bad thing. 2 squared would be 4. 2 to the third is 8. So those points, again, 2, 4 here, 3 being 8 is going to be off my graph. But notice we're going to rise fairly quickly upwards and to the right. The real change comes in, if you think that looks a lot like a parabola, well, the right side might, but the real change comes in at the left. 2 to the negative 1 is actually equal to a half. Remember, negative exponents make for fractions. So 2 to the negative 2 is going to be a fourth. Well, at negative 1, we're at a half. Then we're at a quarter. And as you can see, we're going down. Instead of multiplying by 2, essentially dividing by 2. But remember that no matter how many times you divide by a positive 2, that's never going to turn your number negative. It's also never going to turn it into 0. So what we end up with is a horizontal asymptote, a line we're going to get infinitely close to, but never quite touch, at y equals 0. And that's where that's where your basic horizontal asymptote is going to be for, again, a basic exponential function. Let's try another example, but instead of doing lots and lots of work, let's think about that asymptote first. Again, there's a basic exponential function. So if we put our line at y equals 0, kind of right on that x-axis, what we can do then is use our two easy points. Well, 3 halves to the 0. Again, it's just going to come out equal to 3. And 3 times 3 halves to the first is going to be a 9 halves, or about 4.5. Well, 0, 3, and 1, 4.5 tells me that to the right, I'm going away from the asymptote. So all I have to do then is follow the asymptote, curve up through my points, let the line keep curving upwards, and there is a basic with labels, don't forget to label your axis, exponential function. Taking advantage of that same idea, what do we do when there's some shifting going on? Well, the first thing I would do is ignore the +1 and the -3. Remember, those are transformations. So they are going to take us shifting to the left 1 unit. That's this +1 up here. And they're also going to take us down 3 units. But left 1 and down 1, or down 3, from where? Well, let's first find two easy points. And that's what I'm talking about up here. Let's take our basic function, 1/2 times 2 to the x. We're going to plug in 0. 2 to the 0 is 1, which essentially gives you 1/2. And if I plug in 1, basically that turns into just a times b then. 1/2 times 2, or 1 as well. So you've got your two easy points, 0, 1/2, and 1, 1. But now what we need to do is perform our transformations. So I'm going to shift to the left 1 unit. Well, that takes all my x values, left 1. So 0 becomes -1 and 1 becomes 0. Then I'm also going to go down 3 units. Well, 1/2 down 3, or -3, is -2.5, and 1 minus 3 is -2. So -1, -2.5, and 0, -2, with an asymptote also moving, y equals 0, so I'm going to move that down 3 units, so y equals -3 right here. Follow the asymptote through the points. You get a simple graph, again growing to the right, and there you go. Again, you can always use more points if you want to be a little bit more precise, but the basic idea is there. So that's how to use an initial value and a base to make a graph, also how to use some shifting, and your graph, your sort of basic equation is over there to the right, h and k being your horizontal and vertical shifts, as we've used before. The last thing to discuss is just some of the real-world applications of exponentials. Again, one of the major places we see them is going to be out in the business world. 1 plus r would be called our growth factor. We basically replaced b up here with a 1 plus r. Again, to be exponential growth, what's to the power of x needs to be greater than 1. How much greater than 1, or that growth rate, is actually what tells you how we're growing. So a growth factor is 1 plus r, but the growth rate is how much greater than 1 are we going to be. And one place we could use that, again, is out in the real world here. In 1980, about 2.1 million US workers worked at home. In the next 10 years, the number of workers working at home increased by 5% per year. So if we wanted to write a model where 1980 is essentially t equals 0, what we can say is the number of workers working at home, W, right, will be equal to the initial amount, 2.18 million, times. Now we want to increase by 5% per year, but if all we put was 0.05 for 5%, we're going to decrease. Remember, that's less than 1, so our numbers are going to get smaller and smaller, which is why we need to say 1 plus 0.05 raised to the t. Approximately how many workers were working from home in 1988? Well, for that, we can use our function and say, well, 2.18 times 1 plus 0.05. 1988 is 8 years after 1980, so to the 8th power. And if we go on our calculator, 2.18 times, in parentheses, 1.05 raised to the 8th, we'll find out that there were 3.221, or 3.221 million workers working from home. The last thing we can do is, since we do have a nice model there, we can use that to predict how long it will take to also end up with 4 million workers. Now realize that means we're saying 4 equals 2.18 times 1 plus 0.05 to the t. Since we don't know how to solve these equations yet, we'll get to that in a later section. One thing we can do is go onto a graph. So let's go ahead and add a graphing page. And we can plot the function 2.18 times, again, 1.05 to the x. And if we graph that, we get a nice function there. But then we also want to know, when is that going to reach 4, or when is that going to reach 4 million? So I'm also going to plot another function. Remember, one way to do that is say Control G, get our function menu back up there. And when will our function be equal to 4? Now notice I can't see that on my graph, but remember that I can always click here, and let's move this off to the side a little bit. So we've got that going there. Now we just need to find the intersection point. So if we say Menu, Analyze the Graph, Intersection, I just need to find that point. So we'll click, move to the right, and click, and find out that our point at 12.440 will end up at 4 million. So according to our graph, t equal to about 12.44 years should get us up to 4 million. Again, that was using your graph to find the intersection point of your lines. Hope that helps you solve, and have a great day.